Next, we're going to look at the OpenStack object storage project, which is codenamed Swift. OpenStack Swift has actually been around since the inception of OpenStack. It was in the first release along with Nova as one of the initial packages. You can often see it run out in the wild as a standalone product or project all by itself. It's used for web object storage, which is similar to the Amazon S3 service, or simple storage service. Web objects are different than traditional block files or NFS files. They're not attached to servers. They're simply individual addressable objects, which underneath are spread through a distributed storage environment. It utilizes what we call JBOD storage, or just a bunch of disks, in order to distribute its storage objects and provide redundancy for the files that are spread out throughout them. In fact, you don't want to run Swift on top of a RAID storage environment because the RAID will interfere with the efficiencies of the JBOD delivery. Swift itself is smart enough to already provide redundancy for all its object storage, so there's no need to add additional mirroring. You just simply strap up new disks and new arrays underneath it and then present those into your Swift environment. It's the only project that actually had an in-place upgrade at the Havana release. It's not that it's a direct node per node in-place upgrade, but what it is the nature of Swift. You can add upgraded nodes into the environment and then just decommission legacy nodes and redistribute the objects throughout the new nodes. So you can continuously do these online upgrades and just continue to redistribute until all of your legacy objects and your legacy nodes are gone. You can store files up to 5 gigabytes in size in your OpenStack Swift environment. It's not that you can only store up to 5 gigs, but that's the default. Any file type will work as well. You can configure larger files if you so desire, but tread carefully, because imagine the business case where you say, oh, I'm going to put 100 gigs or I'm going to put no limit on my file sizes. Then suddenly people are storing giant files in this object storage environment, which really isn't the appropriate place to store that. Although there may again be a design case where you could do that, but you just want to tread carefully. Files themselves are not stored as single objects. The file is actually segmented underneath and then spread throughout the distributed storage environment, and there's a manifest file which tracks where all of the subordinate objects are, so that when it's retrieved, it just glues those objects back together and it presents it as a single file to the retrieving requester. The architecture of Swift itself is pretty easy to use, and it's interesting because there's a lot of different topologies you can deploy. In the case of mycyclingstore.com, Jens and Claire decided that they're going to have a public-facing environment. They're going to use this for a content delivery network for the new mycycling.store website, along with a number of other things. So on their internet-facing public switch, they've simply presented IP addresses to their Swift proxy node and their authorization node. Ahead of that, you can put all of your infrastructure in this private area behind it. So this is the good thing, is that security folks love it because you don't have to put all of your storage nodes on an exposed public address. You simply have to have your proxy node be able to access them through the private network inside your cloud environment. And again, this could be public cloud or private cloud or hybrid in a number of different deployments. The files themselves are stored in what in effect is now a file object cloud, which is running distributed across your storage nodes. So you can see there's any number of file types that are supportable. So in the case that Jens has something that he wants to be able to use inside his Swift environment, let's just say he's redesigning the site and he's got a Photoshop file, and he wants to store that in our web object environment. He makes a put request through the API, which is handled by the proxy node, and then it stores the file back into the storage node environment, distributing it across the nodes as it needs to once it actually receives the initial file. The reverse is true for request nodes as well. In the case that you request a document, it's pulled through the proxy node, pieced together, and then presented to Jens as a single doc file just as if he remembered storing it in the first place. You'll notice there that when Jens put the PSD file, there wasn't one there before. But when he retrieved the doc file, it actually left a copy of it behind. That's because it was just that, a retrieval. It wasn't a move operation. In this case, it was a GET request. So if you wanted to remove a file, you would actually put a delete request in. Remember those HTTP verbs and the CRUD that we talked about before? Create, read, update, delete. And in fact, in this environment, we typically only use create, read, and delete. So if he wanted to delete a movie file that we no longer needed because it was fairly large, he would just send in a delete request in for this movie file, and it would just disappear. It's really just that easy. Now, I take for granted how easy it is to administer a Swift environment once it's up and running, but I suppose understanding what's happening under the covers can seem a bit confusing. There's a lot of different configuration sets that are happening within Swift that keep it all working and are part of the whole distributed storage and distributed authorization environment. We have account databases and container databases. These track the accounts and the object pointers which are used for storing the objects and making sure that we know where they are across the storage environment. All of those objects are then put into partitions, and a partition is then assigned 3 different disks in different zones. The reason why it's 3 is similar to what the RAID methodology is it's distributed across a minimum number of nodes so that you can have an n-1 failure. If you're running a purely mirrored environment, you could put it in 2, but that's not the way that Swift works. So all of our partitions are spread into the zones, and you can configure the number of zones that you have. Ideally, you want to have more than 3. 3 is the minimum that you have. But in the case that we have, say, 5 zones in our picture here, if zone 4 were to suddenly disappear because of a hardware failure or some kind of access failure to that storage block, then ultimately the load is just redistributed across the remaining 4 zones that are still alive. All of this comes together to describe what we call the ring. Rings are the environments. These are effectively magical, not unlike, I'm sure, the Lord of the Rings reference to the one ring that rules them all. So the ring tracks where all of these partitions are, and it maintains the replication and the distribution of all these files across the storage. And so ultimately, it connects directly into the storage node itself. Well, we've learned a lot, and we've covered a lot of topics. Unfortunately, we can't go too deep because we don't have that much time. But again, stick with Pluralsight, and you're going to find more great courses specifically on some of these OpenStack storage services. Now that we know what the 3 types of OpenStack storage are, we can easily talk about it and understand it as we look at the different projects. Cinder environments are absolutely important because without block storage, our instances don't live for long. Those ephemeral storage volumes are only good until they disappear. Understanding how Cinder works with vendors is going to be key when you're evaluating your OpenStack solution. You need to be able to know that your hardware support is going to be available from your particular vendor if you deploy OpenStack on top of their environment. And if you wanted to run an OpenStack object storage environment, or Project Swift as we know, then you have a good sense of what it is, and you're comfortable enough to kind of go ahead and find out the deeper workings of how object storage works and how you could deploy it into your enterprise. Now, it's time for us to move on to our next module.